Okay, in this video we're going to talk about probability models. So we have Bernoulli trials. We have Bernoulli trials if there are two possible outcomes, a success and a failure. The probability of success, which we're going to call P, is constant, and the trials are independent. Now, if you can't tell for sure if they're independent, then you can use the 10% condition. This is if the assumption of independence is not obvious, it is okay to proceed as long as the sample is smaller than 10% of the population. So if the sample you're working with is definitely less than 10% of the entire population, then you can go ahead and proceed. Alright, so we have binomial and geometric distribution. So a binomial versus a geometric random variable. So the definition of a binomial, it counts the number of successes in a fixed number of trials of Bernoulli experiments, and geometric counts the number of trials until the first success is achieved in repeated trials of Bernoulli experiments. The notation for a binomial is binom and then the number of trials, comma, the probability of success. And then the notation for geometric is geom and just the probability of success in parentheses. The mean, to find the mean for a binomial, it's n times p, and that's on your reference sheet. To find the mean for a geometric, it's 1 divided by p. The standard deviation follows the formula for binomial, the square root of n times p times 1 minus p, and you'll hear 1 minus p referred to as q. So anytime you see q, it's really 1 minus p. For geometric, it's the square root of 1 minus p divided by p. And then the probability model. So to actually calculate the model without a calculator, for binomial we use this combinations equation. And then for geometric we use that exponential equation there. Alright, so our first example. Computer chips have a 25% chance of being defective. Create a probability distribution for x if x is the number of defective chips in a sample of 3. What is the probability of having 2 or more defective chips? So it can either be defective or non-defective. So I have only 2 outcomes. My probability is fixed, and I can assume that the chips are independent of each other. Okay, so I have a 25% chance. I'm doing 3 samples. So what I would normally do, if I was doing this before I learned anything new, I would make a tree diagram. So I have defective and non-defective. 25% are defective, which means 75% are not. And I'd break that in. That was my first sample, then my second sample, now my third sample. So I'd multiply straight across. So I could have defective, 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 which is 0.01563. And then I could do that all the way across for all my other ones. So there's all my different probabilities in my probability model. So I'm going to put those into a table. So x, the number of defective chips, could be 0. If I have 0 defective chips, then that means that they're all non-defective. Well, there's only one time that happens, and my probability was 0.42188. If the probability has 1 defective chip, then it has 2 n's and a d, and if I add the ones where there's 2 n's and 1 d, it comes out to 0.42188 also. If I add the ones that have 2 defective chips, so it has 1 n and 2 d's, doesn't matter the order, I get 0.14064. And then I only had one situation where all 3 of them were defective, and that was 0.01563. So there's my probability distribution for the computer chips. It is known that only 15% of the population is left-handed. Create a probability distribution for the number of left-handed people in the sample of 3. Check, is the problem binomial or geometric? So they're not asking me to find, so create a probability distribution for the number of left-handed people in a sample of 3. So they're telling me how many it is for. They're not asking me how many until I get the first left-handed person, so that would be binomial. So binomial, my number of trials is 3, and my probability is 15%, so 0.15. So I would use this formula to calculate it out. So this is if you're not using the calculator, which I want to make sure you know how to do it, because sometimes you'll see the formula written out like this, or some method of combinations on your AP reference sheet. Now, where I say N combination K, those can also be stacked on top of each other. So NK, not a fraction bar, but just N over K. So if you're used to using it in that format, you can do that as well. So there's the formula. So I would plug in all those pieces. N is 3, K is the X value for that specific row, and Q is the 1 minus the probability, and P is the probability. And then C stands for combination. So NCR is the button you would press on your calculator to get combinations, which is under math and then probability. Okay, so then my P value is 0.15 to the 0 power. My Q is 1 minus P, which is 0.75 to the N minus K. Well, N is 3. 3 minus 0 is 3. The next one would be 3 combination 1. My probability is 0.15 to the first, and then 0.75 at 3 minus 1 would give me 2. The next one and the next one. So that's how you would write them out if you were doing them long ways. And then calculate them. Make sure you're using the combinations button in your calculator, which again is under math, probabilities, and it's NCR. Alright, so now you're probably not going to want to do that if you have a sample size of 50 or 100. So instead, we're going to use the calculator. So the calculator, if your probability is for a specific value, you're trying to find the probability at a specific value, then you're going to be either doing binomial PDF or geometric PDF. So binomial PDF, and then it's your N, comma, your P, comma, your K value. And then geometric, it's your P value, comma, your K value. And if you have a newer calculator, it will tell you what exactly they're looking for, and you just type it in. If they are asking you to find a probability of it being less than or equal to some value, then it's a cumulative distribution function. So it's binomial CDF or geom CDF. Okay? And if they're asking you to find it where it's greater than some value, then it's 1 minus the CDF of that type of function. So PDF is a probability distribution function given individual outcomes probability. So that's if you're working with an individual value. Okay, and then cumulative distribution function, that's if you're working on a cumulative, so a bunch of values, so less than or greater than some amount. Adds all those probabilities below. And then both distributions are under distributions in your calculator. So it's second bars is what you hit to get distributions, and then you'll see all the binomial and geometric distributions in your calculator. Alright, so geometric or binomial. The situation. People with O-negative blood are called universal donors because O-negative blood can be given to anyone else regardless of the recipient's blood type. Only about 6% of people have O-negative blood. Question 1. If donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O-negative blood? So this is until your first success. So that's a geometric distribution. Suppose 20 donors come into the blood drive. What is the probability that there are 2 or 3 universal donors? So this is finding it for a specific number of trials. So that's binomial. Alright, so our example with the O-negative blood. People with O-negative blood are called universal donors because O-negative blood can be given to anyone regardless of the recipient's blood type. Only about 6% of people have O-negative blood. If donors line up at random for the blood drive, how many do you expect to examine before you find someone who has O-negative blood? So you're going to want to check first that there's success or failure, that there's only 2 outcomes. Okay, I have only 2 outcomes. Okay, they either have O-negative blood or they don't. I want to check that they're independent, and if they're not independent, that it meets the 10% condition. So this sample is surely less than 10% of the population, because my population would be every single person. And the people that are lining up at this blood drive, I'm sure, represent less than 10% of the population. And you also want to make sure that your probability is constant. So my probability is 6%, and that is constant. So this is a geometric distribution with a constant probability of 6%. All right. So my expected value, because that's what they're asking, how many do you expect to examine before you find someone who has a negative O blood? So my expected value, I'm using the geometric distribution for mean, because expected value is the mean, which is 1 over p, so it's 1 over 0.06, which gives me 16.66 repeating. So I would expect it to take 17 about people before I found someone who has O negative blood. What is the probability that the first O negative donor is found, the first O negative donor found is one of the first 4 people in line? So the probability that it's less than or equal to 4. So it's geometric CDF, and then my probability is 0.06, and my K value is 4. So I'm going to go to my calculator, and I'm going to go to second vars, distributions, and then I'm going to look for geom CDF. Okay, so in my calculator, I'm going to go to second vars. That's my distributions. I'm going to go to the bottom, so I'm going to go up to go to the very bottom, and then geom CDF is one of the ones here on the very bottom, which is the one I'm looking for. My p-value was 6%, so 0.06. And then my x value was 4. I'm going to paste that in. And I get 0.219. So that means that our probability that it's the first O negative donor is found in the first 4 people in line is 21.9%. Suppose 20 donors came to the blood drive. Recall that 6% of the people are universal donors. Question 1. What is the mean and standard deviation of the number of universal donors among them? And what is the probability that there are 2 or 3 universal donors? So I know that I have 20 donors, so this makes it binomial. I know the number of trials. So there are 2 outcomes, O negative, I think it was, or not. And then there is a constant probability, which is 0.06, and it passes the 10% condition. So surely the donors that represent are less than 10% of the population. And X value is going to be the number of O negative donors, and N is going to be 20 people. So there's all my conditions. So when you have something where you have to check conditions, you want to make sure you have all the conditions like bulleted out before you start any work. So this is a binomial distribution with an N value of 20 and a percent of 6. So my expected value, which is the mean, is equal to N times P. So that's 20 times 0.06. So my mean is 1.2. They also asked for the standard deviation, which is the square root of N times P times Q, and Q is just 1 minus P. So it's 20 times 0.06 times 1 minus 0.06 is 0.94, which gives me 1.06. Question 2, it says, what is the probability that there are 2 or 3 universal donors? So I would have to find the probability that x equals 2 and the probability of x equaling 3 and add them together. So we're going to do that in my calculator, and here's what I get. I'm using a binomial PDF where x is 2, and then another binomial PDF where x is 3, and I'm adding those together, and I get 0.3106, which I'll show you in the calculator. Okay, so to do this one in the calculator, I'm going to go to second vars, which will give me my distributions. I'm going to go to binomial PDF because I'm finding it for precise values. So PDF, I'm going to do it for 2 and for 3. So my number of trials was 20. My p-value was 0.06 because 6%, and I'm going to do it for 2. Then I'm going to repeat this process for 3. So for 2, I get 0.22457. And then if I don't want to go back and do all those buttons again, I can just go up and copy it, and then change the 2 to a 3, press enter, and my other value was 0.086. So that's where those numbers came from. And then if I add those two, I get my solution. So it said 2 or 3. So copy it and then go up, copy that one, and add them. I get 0.31057. Next question. John is taking archery. He has a 30% chance of hitting the target each time he shoots. He shoots 8 times. So they told me how many shots he took. So that means it's going to be binomial. There's 8 trials. 2 outcomes, hit or miss. So I'm checking my conditions. My probability is constant at 30%. And I'm going to assume independence. Each shot he takes is independent of the last shot. X is the number of hits, and N is 8 shots. So it's going to be a binomial distribution because they told me an N value. 8 shots and a 30% chance. What is the probability that he hits the target 4 times? So exactly 4. So that means my X value is equal to 4. So I'm going to do a binomial PDF, and I'm going to do 8, then 30%, and then exactly 4, PDF, because I'm looking at that precise value, and I get 0.163 or 1361. What is the probability that he hits the target 2 times or less? So the probability that X is less than or equal to 2 would be a binomial CDF, 8, 30%, and 2, which is 55.18%. What is the probability he hits the target at least 3 times? So the probability that X is greater than or equal to 3. Okay, so 1 minus the probability that it's less than or equal to 2 would give me that. So I already know the probability that it's less than or equal to 2 because I just found it. So it's 1 minus 0.5518, which gives me 0.4482. What is the probability that he hits the target less than 5 times? So the probability that X is less than 5, which would be the probability that X is less than or equal to 4. Okay, because we have to have it equal to a value. So it's going to be a binomial CDF, 8, 30%, and then 4, which gives me 0.942. 5. What is the probability that he hits the target more than 6 times? Probability that X is greater than 6. That I can do without the equal to. Is 1 minus the probability that X is less than or equal to 6. So it's 0.0013. How many times do you expect him to hit the target? An expected value is your mean. So I'm finding the average, the mean. So my mean is N times P because it's binomial. So it's 8 times 30%, which gives me 2.4 hits is his average. What is the standard deviation of the number of times he will hit the target? Again, it's binomial, so I'm using the formula for standard deviation of a binomial distribution, which is the square root of N times P times 1 minus P. So 8 times 0.3 times 0.7, which gives me 1.296 hits. All right, your turn. Your businesses are sent mailings asking them to answer a survey question and send the mailing back. The probability of non-response is 55%. So I'd like for you to please try this problem, and I will be grading this problem.